Because plastic shrinks as it cools, all injection molded parts warp. Fusion injection molding simulation helps identify if the maximum deflection or warpage observed is within the specified tolerance for your part. While all plastics shrink, several factors can lead to local variations in how it shrinks in a mold as it cools. When some areas of the plastic part shrink differently from other areas, this differential shrinkage can cause the part to warp. Warpage is the out-of-plane shrinkage or movement that occurs as the part continues to cool after it has been ejected. In this lesson, we will review the deflection and warpage tolerance plots. We will look at the common causes of warpage. For each cause, we will discuss ways to minimize or reduce the amount of warpage by making changes to the part design, gate location, material selection, and process settings. The deflection all effects plot shows the amount of shrinkage and warpage that is likely to occur with the study setup conditions relative to the initial CAD model using the best fit approach. The red areas indicate where the greatest shrinkage and warpage will occur. The range scale shows how much the local area distorts. You can use the magnification tool in the results settings to exaggerate the distortion. If your part has deflection tolerance requirements, you can activate the threshold sliders and move them to see if the result meets your requirements. The warpage tolerant result highlights those areas of the part where out-of-plane deflections exceed the specified warpage tolerance. Adjust the default tolerance shown on the slider to match your part's tolerance requirements to see if the warpage is likely to be a problem. Once you've identified which areas of the part experience higher volumetric shrinkage, you can determine whether changes to the part model, injection location, material selection, or process settings can reduce part warpage. Ideally, your part design should have uniform wall thicknesses. While this is not always possible, when the wall thicknesses vary, the volume of plastic in each area varies, and therefore the amount it shrinks before it freezes can vary. The volumetric shrinkage variations can ultimately lead to warpage that exceeds your part's tolerance requirements. Areas of the part that have thicker wall sections shrink more than areas than thinner wall sections, because there is more material that cools and shrinks. The best way to reduce overall deflection or warpage is to reduce the thickness of these thicker areas. Similarly, and in reverse, you will have warpage concerns where there are areas of the part that have thinner wall sections because they shrink less than the thicker sections. If there are more thicker walls in the vicinity than thin walls, it may make more sense to increase the wall thickness in these local areas to help reduce the warpage. Where you place the gate or injection location affects the injection pressure and can affect the resulting volumetric shrinkage and warpage values. The further the melt travels, the greater the pressure required to fill the part, and the greater the volumetric shrinkage and warpage. Move the injection location to a more central position to reduce the injection pressure, volumetric shrinkage variation, and warpage values. If you have the flexibility, another solution to address shrinkage and warpage problems is to select a material that expands and shrinks less when it is heated and cooled. Amorphous materials typically shrink and warp less than semi-crystalline materials, and you can filter for the material structure in the materials database. Consider cloning your original study so you can compare the results and select different materials with different material structures and lower average nominal shrinkage to see how they can reduce your warpage values. The last variable you can change to reduce the warpage of your part is the process settings. You can adjust both melt temperature and mold temperatures to help reduce the amount of deflection. Typically, you can increase the melt temperature and mold surface temperatures to reduce the amount of shrinkage and warpage. Make sure to keep the melt temperature and mold surface temperature within the manufacturer's recommended ranges for that material, which you can find in the materials database. In addition to the deflection Oleflex and warpage tolerance results, you can also use the flatness tool to see how much the part has distorted. The flatness tool measures the flatness of selected faces relative to the flatness plane you specify. This is useful to understand how well that surface might sit on a flat table surface or whether it will connect properly with another part in an assembly. In this lesson, we reviewed both the deflection and warpage tolerance plots. We identified common causes of warpage and discussed ways to minimize or reduce it by altering the part design, injection location, material selection, and process settings.